So next is another set of speakers from Weyerhaeuser. We have Mark River and Jason Walter. They're going to be talking about the holiday farm fire, impacts on shade, stream temperatures on private timberlands, and impacts to the upstream extent of fish distribution in headwater streams on private timberlands. So I think they're both going to talk one after another and then do questions afterwards. So I'm going to bring up Mark first. Come on up, Mark.
All right, hello, and I'm really glad to be here, excited to talk to you all today. And we're trying to allow plenty of time for questions at the end, but we'll hold the questions till after Jason's talk. So I'm going to talk about mostly focused on stream temperature on private land, but we do have some other data that I want to kind of throw out as well. So if I show you something that's not temperature, you're forewarned here. And I really want to acknowledge this has been a real team effort, and I want to acknowledge Pete James, Jason, Renee, Travis, and Miranda, who have been a tremendous part of this. Okay, so we're kind of thinking of this in kind of three buckets, if you will. The immediate effects of fire on the stream temperature. So as that fire was actually rolling through those few days where it was burning really hot, what actually happened right then? And I'm going to reference a Sanders et al. Paper for that. What I'm going to mostly talk about today is what we're considering more the short-term window. So this is the year of 2021, the year after the fire, and what really happened there with stream temperature and some other metrics. And then we're also considering a longer term, kind of that year two on, 5, 7, 10 years into the future, and I'll lay the groundwork for that a little bit today too. I'm also just going to mention some shade and some sediment and turbidity data that we're collecting also. So we've heard a lot in the talks about burn severity, different ways of measuring burn severity. Is it canopy cover? Is it the basal area? Delayed mortality effects. We had some great talks talking about that. So there's a lot of different remote sensing products, probably not one kind of perfect product for this. But what we're looking at is, for this project, at least at this initial cut, is canopy cover mortality. And I've got the website lined up there for it. And we heard yesterday the talk about kind of that bathtub ring, if I'm phrasing that correctly. This where you have the real severe, largest portion of the fire, and then these kind of rings outward. And we definitely see that in this holiday farm fire. This is where a lot of our sites are. The red is the severe burn. And some of our watersheds are just almost entirely covered in that severe burn area. But we do also have a lot of sites on the fringe. And this here, if you're familiar with this area, this is the Gate Creek, Calapooya River divide. And that fire really burned hot all through that Gate Creek watershed, and then was much cooler once it got into Calapooya. So there's some interesting sites through there. But the biggest takeaway is a lot of these sites are in a very severe burned area. And here would be an example of kind of a younger stand in that fire. This would be maybe roughly 10-year-old stand, and don't see too much live vegetation out there. And this would have been maybe March or so of 2021. So just to kind of give a feeling of, what that looked like on the landscape on private timberland following that. So this is a really interesting project. David alluded to this in his talk earlier that, post-fire, if you're looking at stream temperature or some other metrics, one of the challenges is pre-fire data, right? I mean, you can always go out after the fire and instrument, but sometimes it's difficult to analyze your results if you don't have the pre-fire data. So really this is an opportunistic study that we have here I'm talking about today. And the reason that we're able to do this is that we had quite a network of pre-fire monitoring data. Of course, we didn't know this was ever going to burn. That wasn't the intention. These were just sites that were set up for monitoring stream temperature long-term. Weyerhaeuser has these throughout Washington and Oregon. And this area, if you all knew Marianne Ryder, who was my predecessor at Weyerhaeuser, I know a lot of you knew her. She actually didn't live too far from here and work too far from here, so we had a really dense network. This was kind of in her backyard, so to speak, and she had a real affinity for this area. So we had a really dense network of monitoring locations, and then it just happened to be that this is the area that burned, and so I've overlaid the Holiday Farm fire footprint here, which is this kind of red dashed line, over our long-term stream monitoring sites. And what's pretty cool about this is that we had some sites that are like I showed on that previous burn severity site, kind of right in the heart of it, and first couple days of that fire when it was just raging through there. We have several sites that were right in the thick of that. But we also have a lot of sites kind of on this periphery, or where, part of the watershed is in the periphery, part of it's in the burn. And then we also have some sites nearby that didn't get burned at all. So we actually have some kind of true control sites, even in an opportunistic study like this. And so I think that makes this a unique opportunity to kind of take a look at some of these stream temperature metrics. I also want to point out, we did also go in and install a couple of climate stations after the fire, both for our operational team, safety-wise, so they'd know if there was too much precipitation to get out there safely and work, but also for our research purposes, just to get better information on primarily air temperature and precipitation on this. So we do have those that are installed that helps us with our analysis. I also want to give a shout out to Noah. I don't know if Andy's here today, he was here yesterday, but Noah also put in a weather station in Gate Creek. You can see this is in a real severe part of the burn. It's right, we tried to put it right kind of where that snow line would stop. I think we hit it pretty good. You can see it was a little snowy. We're out there doing the install. But this is public data, so this is accessible, whoever wants it. I can give you that link after the talk if you're interested, but this is one of NOAA's kind of short-term or intermediate-term weather stations, and that data is available. And you can just also, maybe I'll just point out here, you can kind of get a feel for, what that Gate Creek watershed looked like, kind of at the more of a landscape scale following that burn. And we put the climate stations in these kind of more open areas as open area. They tend to be pretty younger stands that burn severely. So I want to give a shout out to Ashley Sanders' 2022 paper. If you haven't read it, it's really cool. I see Ashley back there today, so hit her up if you're interested in this. I definitely recommend reading it. Really cool, and I mention it here because it sets the stage for some of the data that Jason's going to present here in a little bit. But essentially, this looked at what happened immediately when that fire was rolling through. And one of the big things the paper analyzes is the smoke effect, all of that smoke, days and days. Anybody that was living in the Willamette Valley was suffering through it for a couple weeks there after that fire. And just to make a long, really excellent paper into just a short distillation, most of the sites, except for maybe one of the smaller streams, showed a decrease in stream temperature during the fire, and then for that couple weeks thereafter with that big smoke plume that was blocking some of the solar radiation getting to the stream. So our takeaway from that is that actually the streams, if anything, cooled, maybe an occasional hot spot here or there, but in general, cooled for a couple of weeks. And so Jason will talk more about the fish effects of that. And then I mentioned that we also have some turbidity data, which also, of course, can affect fish. And I don't want to spend too much time on this today. Ashley Coble and I will be writing this up here at some point. But I wanted to give a shout out to Ashley Sanders and Ashley Coble, who are really integral part in getting this project off the ground. And one of the takeaways we have from this also is a turbidity suspended sediment relationship that we're going to use moving forward with just turbidity sensors in the stream and still be able to estimate the sediment load and export from that. And David mentioned we've had a couple of dry years after the fire, so we haven't had tremendous sediment export, but we did have a couple of fairly wet events just immediately that first winter. We had about a 4-inch rain event over a couple days, and then there was about a 3-inch event also. So we did actually get some sediment export, and we were able to capture that and get our relationship established. So that'll maybe be a future presentation paper down the road. Also, we have some shade data. I'm not going to dive into this too much today. David presented some nice data in his talk, but I'd say our shade's pretty comparable to what David saw. This is just kind of wanted to give you an example of how this works. Again, we had some pre-fire data. These were just normal monitoring sites, and this would be kind of a typical, like, bigger main stem. This is the South Fork of Gate Creek, which is a large fish stream. It's a pretty good sized stream, and this would be a fairly typical shade on something like this. You can see you get a lot of the canopy cover, but on these bigger streams, oftentimes there'll be a gap in the middle. But this is that exact same site after the fire rolled through in that severe burn area. So this got calculated out at 24% shade. And you can see, there's a few, surviving conifers back there. Those may, die in the future. This kind of standalone, probably not all those will survive. So that shade value could actually decrease, in the years to come before the shrubs grow back in on that. Okay, so let me now get to the stream temperature part of this. We've got 21 sites that we had pre-fire data, and we've clustered these into kind of different burn severity categories based on what % of the watershed burned at a severe rate based on that canopy loss. So I've got unburned, low, medium, and high categories here, just to kind of give some visuals. And we go back to 2010 for our pre-fire data. So we've got 10 years pre-fire data on most sites, some not all that amount depending on the installs. And then we have the 2021 year. We're excluding 2020, the year of the fire, for this part of the analysis. And what we're also trying to capture with this is any kind of trends in stream temperature that we had over the last 10 years, right? Is it warming? Is it not? Do we need to incorporate that into our model of stream temperature response? So the dotted line is any kind of like extension of the existing trend that goes back to 2020. And then we've put a little star on the 2021. And so what you can see is on the unburned sites and most of the low burn intensity sites, you know, these 2021 data points, even though that was a really hot year and pretty low flow year. So in the absence of the fire, we'd expect that to be in the upper end of the spectrum of what we'd have for the previous 10 years because it was a fairly hot, dry year. But you can see most of those blue stars are in line with the trend that we had been seeing. And then in the low burn severity watersheds, kind of same thing. Most of those are kind of within our confidence interval where we think those points should be. But once you start getting into these medium and high burn severity watersheds, you really start to deviate from the trend, you know, that you've had. If you look at these, kind of the purple and the orange, you know, some more than others, but they're all now starting to get outside of that trend line, outside of that confidence interval. So it's kind of one way to interpret the data, and we also built this into one of our models here. I just want to also, for visual purposes, show kind of the standard box plot in these same categories. You know, the gray is all the pre-fire data, that 10 years going back 2010, and then the red is the 2021 data in these different categories. And you can see that, you know, as you get more and more severe burn, you really start to deviate from those pre-fire conditions on the different watersheds. Okay, I want to present here the results of a couple ways of analyzing this data as to, okay, what was the fire effect on the increase in stream temperature? One way in the orange here is just a standard before-after control impact analysis, so just pretty straightforward. And then we also looked at an alternate, a linear mix model, which we essentially build into that temperature trend that I was showing there and factor that in addition to the impact of the burn. And the main takeaway from this is that both ways we look at it, we get pretty similar results, right? If we burn really hot and severe, we were getting close to 4 degrees difference on the 7-day average max metric, which is kind of in line with some of the other temperature data that we've heard about here today. And then as you get, you know, closer to the unburned, it gets lower, maybe 1.5 degrees, and then down under 1 degree. And here's, for the linear mix model, here's the actual standard error and our estimate in the increase. So, but it's pretty similar either way we look at that. But you know, maybe 4 degrees increase on the 7-day average max, and like David and Brooke mentioned, that means a daily, you know, one daily value might have been 5, 6, 7 degrees on those really hot days that rolled through. So we do have 21 different sites. This is just kind of the raw data, just showing how we clustered in the different categories. You know, of course, we also have watershed size and elevation, which some previous work, you know, has shown can make a difference in the absence of fire to stream temperature. So we would like to try to build that into our model moving forward. That's something that we're working on in the current manuscript that's under development, and see if there's any interactions between fire and watershed size or elevation, you know, how those might factor into the response that a watershed sees to fire. Also longer term, in this kind of understanding the long-term impacts of fire and stream temperature and shade, and how that maybe recovers back towards baseline over time, we added about 100 new stream temperature sensors in the Holiday Farm Fire footprint and around the perimeter, and 15 new shade sites. So that gives us about 120 different sites for stream temperature and about 30 sites of shade. And we're going to be monitoring that over the next 5 years or so, and then kind of reevaluate how far we want to go with that. But you can see this is Gate Creek Watershed. We've pretty densely popped these in, including 24 of them that are in line with the uppermost point of fish distribution. So we'll be able to get a really good feel for, you know, those uppermost fish points, what that stream temperature is doing over time. So with that, I'm going to wrap up my part of the talk, and again, acknowledge all the people that have worked really hard on this project, and hand it over to Jason. Thank you.